Real quickly, I forgot to mention at the end of the last video that, of course, what you're finding here is mass. So you just found that the mass is equal to negative 4 e to the negative 1 plus 4 grams because the density was grams per cubic centimeter. And see, the cubic centimeter part is taken care of by the dy, dx, dz because those three are all measured in centimeters. So centimeters times centimeters times centimeters makes centimeters cubed. So when you integrate the grams per centimeters cubed times centimeters cubed, all the centimeters parts cancel, and you're left with just grams as your unit. Sorry, I should have put that in there. So the mass is about 2.528 grams. All right, now let's do one last problem in this section. We're going to find the mass of the portion of the cylinder 9y squared plus 4z squared equals 36 that lies between the planes x plus z equals 6 and, sorry, this was a typo, it should be 2x minus z minus 8, given that the density is 4 grams per centimeters cubed. Okay, well, that's a lot going on, so let's see here. First thing I did was I wanted to graph the thing. So it's a cylinder. It's a cylinder. It's stretched in the x direction because there's no x in here. So it's in the x direction. And it's cut across by two planes. You have the x equals 6 minus z plane. And then I solved this plane for x as well because I figured since there's no x in this thing, I'm going to have to do this with respect to x since it's stretched in the x direction. So I solved this for x and I got x equals z minus 8 over 2. And in case you're curious to see what it looks like in Maple, I graphed it. So it's a cylinder, right? And it's got two planes that are hacking across it, right? So you got the one plane, which is, let's see, what color did I make it? So one plane is going one way, 6 minus x, and then the other plane, 2x plus 8, is going in the maroon direction. There you go. And then that cylinder, I wanted to do it in plot 3D, so I actually did it this way. So negative square root of 30, so I solved it for z, in other words, because plot 3D is automatically a z. So that's what I did. So I solved everything for z in order to be able to graph it, but I don't necessarily want it solved for z in order to be able to do the problem, if that makes sense. So when I'm plotting, I wanted to be able to plot easily, and I love plotting with plot 3D. So I solved this one for z, I solved this one for z, and I solved this one for z, and that's how I plotted them. Now, is that the only way to plot? No. You could also do implicit plot 3D, which is a little bit easier in this case because then you can just type in the functions as given. So there they are as given. I still have the cylinder, you can see, and I just chose to, gave it some numbers and chose where to go from. I've got that blue one and I've got that maroon one. Believe it or not, it's the same graph as what's up above, but you're looking at it from a slightly different frame. Obviously, the axes are very different. All right, so that's what we're trying to find. We're trying to find the mass in between these planes. So if you see that cross section in there, you're trying to find the mass in there given that the cylinder has a certain volume that was given to us. All right, well, one thing I'm going to need to know is I'm going to need to know the shadow that I'm going to cast. And since this is obviously stretching in the x direction, then the shadow I'm going to cast back is onto that YZ plane. You can see it right there, right? If you're going to look down the barrel, you're going to look right down the barrel of the x-axis, right? And then there you have it. Although apparently I did this wrong, but you know what I mean. You can really see it in this graph right here. So you're looking right down there. And you can see if you cast that shadow back, I mean, look at the cylinder. When you cast it back, it's going to be a circle, right? Now, how would I prove that? Well, I'd take this part right here and I'd solve it for, say y, for example. You can solve it for z, it kind of doesn't matter. But I'm going to solve it for y. Oh, it's actually not a circle. That's an ellipse, right? So it's an ellipse, and that makes sense because when I'm looking at the maple graphs, it's not quite perfect, especially down here on this one. You can see it's kind of an oval shape. Got it. All right, so we have an ellipse kind of shape. So then let's prove that. How does that work? Well, you would solve it for y. You'll get y squared, 9y squared equals 36 minus 4z squared. That means y squared is 36 minus 4z squared all over 9. Then you take the square root of both sides, plus or minus, and you would get the square root of 36 minus 4z squared over 9, which is the plus or minus the square root of 36 minus 4z squared all over 3. And you're thinking, why would I want to do that? Well, because you need limits of integration. That's why. So you need limits, and you need to figure out which direction you're going to go. Now, did I have to go this direction? No, I did not. So I know it's an ellipse. It's an ellipse that's got more in the z than it does in the y, for example, and that you would get that if you divided everything by 36, right? So if you remember your conic section stuff from pre-calc or calc 2, right? So if I divided everything by 36, I'd get an ellipse. It would be longer than it is tall, blah, blah, blah. But I need limits of integration. It's not good enough to know it's an ellipse. I need to know what its function values are. So I'd have to solve it explicitly for either y or z. So I chose y, and then I'm going to let the z be the constants from -3 to 3. So in other words, I'm choosing horizontal bars. If you wanted to, you could have solved it for z, and then let your y go from -2 to 2 and do vertical bars. Either way would work. It kind of doesn't make a difference. But you have to pick one. And you have to solve it, I'm sorry to say, explicitly so that you can have some limits of integration. Speaking of which, there's my limits of integration. You can see the -3 and 3 dangling right there because those are for the z. And then the x's, oh sorry, that got up there. The x's are going to be, or sorry, the y's are going to be the thing we just solved for. The negative square root of blah, 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 and then the positive square root of blah, blah, blah. Sorry, I'm going to be really official about this. So I'm taking that function and I'm using it. And then the density was 4, which is a constant, which is nice. That means my integrand is just 4, so that's beautiful. So I've got my z going from -3 to 3, my y, that's the hard part. I had to solve all that junk and get 2 y explicit functions so I could get my ellipse. And then my density is 4. The only thing I haven't dealt with is the x. Oh, but I did deal with it over here because I solved this equation for x right there, and that's the blue one. And I solved this equation for x, and that's that pink maroonish one. And that gives me my 2 values. And the only thing is you have to figure out which direction you're going. But of course, you're going to be increasing for your x. You're going to start with your lower values, which is over here on the maroon side, and working your way up to the blue values. And you can see that in maple as well, right? You got your maroon on your low side, you got your pink on your high side. And then over here, this one, I think this one's actually a little bit easier to see. You got maroon on the low, pink, blue on the high, and you're working your way along that tube from the x value of low at the maroon to the x values high at the blue. So that's why I have the pink one, z minus 8 over 2, which is a half z minus 4, if you want to see it, all the way up to 6 minus c, right there. Okay, so I'm going to integrate 4 with respect to x. So that should be relatively easy. That's just 4x, right? No problem. So 4x, I'm going to go from these two x values, from z minus 8 over 2 to 6 minus z. So I'm going to substitute those in. I still haven't messed with my y yet. I mean, this is not an easy integration to do. All right, then, oops, sorry. Let's see here. So from negative that to positive that. So I'm going to kind of combine, maybe make things a little bit easier on myself. Yes, I did. So I'm like, you know, who wants to mess around with this? Nobody. So I pulled the 4 out in front. See the 4? I just pulled it out in front for a minute. But then I thought, why don't we figure that out? Because 4 times 6 is 24. 4 times negative z is negative 4z. 4 times a half will cancel and leave me 2. And that 2 times z will get me negative 2z, and a minus 8 times 2 is 16. So if you will, I'm kind of combining my like terms and making this all simplified, and lo and behold, it becomes 40 minus 6z. Great. So now I'm going to integrate that with respect to y. Well, that'll be easy because there's no y in it. So when I integrate with respect to y, it just means putting a y out in front. And then I'm going to go from y equals negative square root of a bunch of junk to positive square root of a bunch of junk, all divided by 3. And then I'm going to substitute those values in for y. And it's going to leave me with a giant mess. But these two are actually like terms. When you minus a minus, it's actually going to add them. So there's 2/3 of that square root. And we are just going to make maple do that. We do not do integrals like that for fun. No, 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 no. We are going to make maple do the hard work. And here it is, in case you wanted to know. So I did it longhand. I actually did the original integral as given. So 4, where x is going from z minus 8 over 2 to 6 minus z, y is going from that square root to that square root, and z is going from negative 3 to 3, and I get 240 pi. When I do it numerically, I get 753.98. And then that last integral that I just showed you is this, from z equals negative 3 to 3, and sure enough, it gives me the same answer. So I know I did it correctly. Now what are my units? Oh, it's grams because this is mass that we're finding. And the density function was grams per centimeter cubed. But the centimeters cubed gets knocked out and canceled by the dx, dy, dz because they're all in centimeters. So the centimeters cubed cancels with those centimeters cubed, and it leaves me just grams as my unit. And that's why it's mass and just grams at the end.